Hey, in this video we're going to be talking about power series. Now, everything that we've done up until now with sequences and series have kind of led us toward this particular section. And this particular section is actually going to be guiding us toward the next few. We haven't really dealt with functions so far. But in this particular section with power series, we actually are going to be dealing with functions quite a bit. Because even before we read through the entire definition, we can actually notice that with power series, we have the return of this letter that's been missing for quite a while, x. So what we're going to be doing from here on out is actually trying to see if we can turn functions into series and relate series into functions and vice versa. This is a concept we're going to be exploring in the next couple of videos, but let's start focusing on this new definition. A power series is a series that has this particular form. We add up a whole bunch of terms where each term has the x's, these variables, where they are increasing in size of their numerator, in size of their degree. This should look very much like a polynomial, because polynomials look exactly like this, except with our power series, we have this dot 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 at the end, which means it's kind of like a polynomial that just keeps adding more and more and more and more and more and more terms. So many terms that it just has infinitely many terms. That's what power series are. They're kind of like infinite polynomials. We actually even have the same names for things. X is called the variable. C sub n, all of these, C sub 0, C sub 1, C sub 2, C sub 3, all of the C sub n, we call these coefficients of the series. And we actually say that the sum of a power series is a function. It's a function that has a particular domain, because anytime you introduce some sort of a function, we have to talk about its domain. Functions have domains. In this case, the domain is all of the x values so that our particular series converges. So we've been testing for convergence for quite a while. We haven't always cared about the actual sum of a convergent series, but we are very, very concerned about whether that series converges or not, and here is no different. We actually want to know how to determine whether this particular power series converges or not, because if it does converge, then we actually have a value that's in the domain of our power series. Let's start off with a nice and simple power series. Let's look at example 1. What is the domain of the power series given below? The power series for g of x, which is equal to a sum. I want you to pay particular attention to our index. Our index does not actually start at 1 here. Our index did not start at 1 in our definition of a power series. It was starting at 0 in each of these particular cases. And so we're actually going to be looking at a lot of series that now begin at 0. So, g of x is defined as the sum as n goes from 0 to infinity of x to the power of n. We're adding up consecutive powers of n, of x to the n. That is, we're looking at 1 plus x squared plus x cubed plus x to the fourth, and I think you get the idea. This is a power series. If we look at the coefficients of our power series, these are the numbers that are multiplied by x to the power of n. In this case, there's nothing there, which means that all of our coefficients are really just 1. So this is kind of like one of the most simple power series that we can come up with, and here we have it. We actually want to know what the domain of this particular power series is, and we need to go back to all of our previous knowledge about series and trying to figure out when a series converges, when a series diverges. So notice that this series actually has a form that's kind of familiar. We have something raised to the power of n. Anytime we have something raised to the power of n as the sum end of a series, we have a geometric series. So we need to go back and try to think, what are the conditions of a series that's geometric that will be convergent? And it turns out, for a geometric series, when we're looking at summing up ar to the n minus 1, as n went from 1 to infinity, then we're actually only concerned with our value r, which was our ratio. And for a geometric series to be convergent, r in size had to be smaller than 1. This meant that our series, our geometric series, was convergent. So what plays the role of our ratio in this particular case? None other than our variable, x. So in our case, instead of looking at r being less than or equal to 1 in size, or less than 1 in size, x has to be less than 1 in size. For power series, we're going to have a lot of fluency in translating between absolute value inequalities and nested inequalities, or just strings of inequalities. But in this case, the absolute value of x is less than 1 corresponds with the nested inequality that x is between -1 and 1. And just so that we will be looking forward quite a bit, we're going to be dealing with intervals a lot in this particular video. So let's go ahead and express -1 is less than x is less than 1 as an interval. That is the interval from -1 to 1. Something that was also nice about geometric series is that if we had that the absolute value of r was greater than or equal to 1, we actually ended up with a divergent series. And so we now know definitively that if x is anything other than a value between -1 and 1, not including -1, not including 1, then we would actually get a divergent series. The only values for which this series will converge is making sure to have an x value that's between -1 and 1. So our domain is the open interval from -1 to 1. All right. These aren't the only power series that we're going to be encountering. This is one very nice type of power series, but we can actually expand the definition of power series so that we actually account for some flexibility. Here's our new definition. Let's say we have this particular series, a sum as n goes from 0 to infinity of c sub n multiplied by not x to the n, but x minus a to the power of n. Now, if you think way back to maybe pre-calculus, then hopefully you remember something about function transformations and translating. If you took x and you replaced it with x minus a, then the effect is that its graph would move to the right a value of a. In this case, it's a shift. It's centering something in a different place. So we take that language about centering and we apply it to power series. The only difference between our two definitions of a power series here is that instead of having x to the power of n, we have an x minus a to the power of n. So we still have a power series, but instead of our power series being kind of centered at what, well, if we take a and replace it with 0, then we would get our power series up here. Instead of our power series being centered at 0, we can center it in some other place. Notice, there's a little bonus, halfway point between -1 and 1, the center of this interval would be, center of this interval would be 0. This is actually an important fact that we will focus on in a little bit, but we will get there when we get there. When we have a power series that is centered elsewhere, we call it a power series centered at 0. Sometimes people say it's a power series about 0, or it might not have to be 0, it could be a. We call it a power series centered at a, or sometimes a power series about a. Now, one other thing that we actually need to make sure that we understand is that up here we're looking at c sub 0 as being the coefficient for x to the power of 0. And we also know that some numbers raised to the power of 0, those are typically just 1. But something that we haven't ever really talked about is what happens if you get 0 to the power of 0. This actually is a slightly complicated expression that we don't ever really deal with, and it's kind of swept under the rug, and that's unfortunately something that we're going to kind of continue to do here as well. We're going to adopt this convention that 0 to the power of 0 is 1. And we're going to continue this down here and say, if you have x minus a to the power of 0, that's going to be equal to 1, even if x is equal to a, in which case we would end up with that nasty form of a 0 to the power of 0. For our purposes, we are going to consider this the value of 1. So let's talk about this new function. Let's try the same kind of thing and try to find the domain of this new power series. Z of x is equal to a sum as n goes from 1 to infinity of n factorial x to the power of n. So in this case, our coefficients are n factorial. It's really nice a lot of the time to take your series, take your power series, and just expand it, write a few terms. This is already done for us up in this previous example, example number 1. But let's actually write the first few terms of example number 2. So we have z of x is equal to a sum, as n goes from 0 to infinity, of n factorial x to the power of n. When we expand this out, we plug in 0, we get 0 factorial, which is just 1, x to the power of 0, which is just 1. When we plug in 1, we get 1 factorial, multiplied by x to the power of 1, which is just x. Then we get 2 factorial times x squared. Then we get 3 factorial times x cubed. And then we get 4 factorial, x to the 4th. And you typically just want to write enough terms so that you really can see the pattern. Remember, this is for you to just try to get a little bit more information about this particular series. I think that seems to be enough to show the pattern. If you want, you can even come back here and put a factorial symbol next to this 2. 2 factorial is 2, but just to see that pattern, we can put that factorial symbol there. So here's another view of the same sort of a function. Let's try to find the domain of this. So we're trying to figure out for what values does of x, because domain happens to be what values of x we're looking for. We're trying to figure out what values of x leads to this being a convergent series. Now for the previous example, we noticed that we had a geometric series, so we were able to determine convergence using that geometric series test. But here we don't have a geometric series, we have some other series. Something that we've seen in the past is that we have a whole bunch of different strategies for how to approach convergence or divergence of a particular type of series. Here, I want to point out that we have this n factorial, and one of the main series tests to use when you have n factorial is the ratio test. So, let's try the ratio test on this particular series. The ratio test is going to say, let's look at the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. Well, in this case, a sub n plus 1 will be taking our summand n factorial times x to the power of n and replacing the n's with n plus 1. So we'll have n plus 1 factorial times x to the power of n plus 1. In the denominator, we just have n factorial times x to the power of n. Now, we've seen this factorial business happen before with the ratio test, but let's just remind ourselves how n plus 1 factorial over n factorial actually works. So we're going to step over to this side and let's look at n plus 1 factorial divided by n factorial. Now what does n plus 1 factorial mean? It means take n plus 1 and multiply it by n, which is 1 less than n plus 1, and multiply this by whatever 1 less than n, which is n minus 1. Multiply that by whatever is 1 less than n minus 1, which would be n minus 2. And then we continue this process until we are left with 2 times 1. In the denominator, we have n factorial, which says start with n, and then multiply by whatever is 1 less than n, which in this case would be n minus 1. And then multiply by whatever is 1 less than that, which in this case would be n minus 2. And then we continue that pattern until we get to 2 and to 1. The ratio test is really, really good with factorials because you get a crazy amount of cancellation. In this case, we can see that we get these n's cancel, these n minus 1s cancel, n minus 2s cancel. Everything cancels with the exception of our one last factor of n plus 1. Alright, so now that we've determined that n plus 1 factorial divided by n factorial is simply n plus 1, we can come back over here, and we can see that we're going to get a good amount of cancellation here. When we look at this limit, we're left with the limit as n approaches infinity. Well, n plus 1 factorial over n factorial, that's just n plus 1. X to the n plus 1 over x to the power of n, that's just x. And so when we're looking at our limit, we're going to be left with absolute value of n plus 1 times x. Well, n is always positive, so if we add 1 to n, we are going to get something that's positive. Well, I apologize, I should go back to say n could actually be 0, which is not positive. But if we add 1 to 0, then we get something that's positive. So we still end up with the same conclusion, that n plus 1 is completely unaffected by our absolute value. X, on the other hand, absolutely is affected by our absolute value because x is a variable. So this same limit can be viewed as the limit as n approaches infinity of n plus 1 multiplied by the absolute value of x. Now we're left with one big limit. Our limit says, what is the limit as n approaches infinity of n plus 1 multiplied by x? Well, if x is some positive or negative constant, then the absolute value of x is going to be some positive constant. And if we take the limit as n approaches infinity, and we multiply it by a positive constant, we're going to get an infinite quantity. So this looks like this is going to be infinity. But are there any values of x that would actually make this not infinity? Well, it turns out, if x happened to be 0, then we would get n plus 1 times 0, and we'd get some numerical value multiplied by 0, which is just going to be 0, and the limit, as n approaches infinity of 0, would actually just be 0. So we don't really get infinity, we don't really get 0, but we get something that's conditional. The condition is exactly what we are looking for. What we end up with is, if x is not 0, then the limit, as n approaches infinity, of the absolute value of n plus 1 factorial times x to the n plus 1 over n factorial times x to the n, this happens to be infinity. And if we remember, we're using the ratio test, and the ratio test says if you get a limit that is not less than 1, then we get that this series diverges. However, if x actually is 0, then the limit, as n approaches infinity, of the absolute value of n plus 1 factorial x to the n plus 1 over n factorial x to the n, this is actually 0, which is less than 1. And so we can say, by the ratio test, our series, z of x, converges. Therefore, the only value of x that actually leads to us getting a convergent power series is 0. So the domain of z of x is a very uninteresting domain. It's just the number 0. So we have two very different results here. We have a result where we had a domain of negative 1 to 1, and we have a result of a domain that's 0. Power series can have wildly different sorts of domains, but here are two very different possibilities. We have an interval, or we just have a single point. Because I mentioned we are going to be dealing with intervals quite a bit, I just want to give you a little bonus and say, if you want, you can represent the set of just the number 0 as an interval from 0 to 0. It's very, very uninteresting, but it might be something that's useful a little bit later on. Let's try this third example. Something that looks quite a bit different. We want to know what is the domain of c of x, which is a sum as n goes from 0 to infinity, of negative 1 to the power of n, x to the 2n, over 2n factorial. So here we have kind of the same sort of a deal. We have this power series. We have some coefficient multiplied by some power of x. We want to try to figure out when does this particular series converge, when does it diverge. For the first example, we used geometric series test. For the second example, we used the ratio test, and we had different reasons for doing each of these. In this example, we kind of have a couple different options. I see an alternating factor here of a negative 1 to the power of n, so I might want to use the alternating series test. But the disadvantage of using the alternating series test is that it tells us when the series converges, but it doesn't necessarily tell us when the series diverges. So there are other series tests that are a little bit better. Usually you want to try to aim for a series test that will tell you both whether when the series converges, also when it diverges. So I see this other factorial here, and that factorial to me tells me that I might want to actually use the ratio test. Just as a little tip for you, I think the ratio test will usually do a really good job at determining domain of a particular power series, but we do want to talk about why we're using that particular test. In this case, we see this factorial. So let's use the ratio test. We want to look at a limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. If you have a fraction, then I think it's typically best to actually view this as a limit as n approaches infinity of the absolute value of a sub n plus 1 multiplied by the reciprocal of a sub n, so that we can actually maybe set this up into some cancellation and we don't have to deal with any complex fractions. In this case, a sub n plus 1, we're replacing all the n's with n plus 1, so we get a negative 1 to the n plus 1 times x to the 2 times n plus 1 over 2 times n plus 1 factorial. This is multiplied by the reciprocal of a sub n. I like this reciprocal business because this entire thing actually is a sub n, so we can just look at the reciprocal of that. We don't have to do anything else. This is 2n factorial divided by negative 1 to the n times x to the 2n. So, when we're trying to compute this particular limit, we want to see if we can get any cancellation of any sort. We want to see what's actually necessary, what's not. And another thing that's really nice to point out is that when we're dealing with the ratio test, we're dealing with a whole bunch of things that are multiplied. We have factors, lots and lots and lots of factors, and then we're taking the absolute value of those factors. When we're taking the absolute value of factors, we can essentially just say, hey, this negative 1 to the n plus 1, depending on the value of n, this is either going to be a positive 1 or a negative 1. But if we're taking the absolute value of this, then the absolute value of negative 1 is 1. The absolute value of positive 1 is 1. This really is just 1. And the exact same argument can be made for this negative 1 to the n. These are each just 1. So we can rewrite this limit, and we really don't need those particular factors. What we have is an x to the 2n plus 1. We can distribute that 2 and say that that's an x to the 2n plus 2. We have a 2n factorial. Can't really do too much with that, so we just have a 2n factorial. In the denominator, we have a 2 times n plus 1 factorial. That's 2n plus 2 factorial. Following our order of operations, we can distribute that 2 inside the parentheses. And then, as our last factor, we have an x to the 2n. Now, again, We use the ratio test with factorials because we get a lot of nice factorial cancellation. So let's look to the side here a little bit and look at 2n factorial over 2n plus 2 factorial. Now, 2n factorial, I'm just going to leave that written as 2n factorial. But in the denominator, we have a 2n plus 2. Multiplied by 1 less than that, that would be 2n plus 1. Multiplied by 1 less than that, well, that's going to be 2n. Multiplied by 1 less than that, well, that'll be 2n minus 1. And we continue this process till we get a 2 and a 1. But look, 2n times 2n minus 1, all the way down to 2 times 1, that's 2n factorial. So we can actually see this 2n factorial is the same as this 2n factorial in the numerator, and we get these cancellations, so all that would be left is just a 2n plus 2 in the denominator multiplied by a 2n plus 1. So, when we look at our limit over here, we get that this should be the same as a limit as n approaches infinity. Our 2n factorial and our 2n plus 1 plus 2 factorial end up with just a 2n plus 2 times a 2n plus 1. On the other hand, we have an x to the 2n plus 2 over an x to the 2n. That just leaves an x squared in the numerator. Just to see that detail, I want you to remember that if you have x to the m divided by x to the n, then by the laws of exponents, this means that we have an x to the m minus n. So in our particular case, we had an x to the 2n plus 2 over an x to the 2n. That should be an x to the 2n plus 2 minus 2n. Well, that's just x to the 2. So just to zoom in or kind of see that detail played out. All right. Let's continue this limit computation here. We have a limit as n approaches infinity of this particular expression. Now, just like before, the 2n plus 2 and the 2n plus 1 in the denominator, those are definitely affected by this limit because it is a limit that involves n's. But this x squared is not really affected by the limit because the limit doesn't have to deal with x, the limit has to deal with n's. So we can take that x squared, and we don't really need to consider that as part of the limit. We have an absolute value of x squared that's unaffected by this limit, but everything else is definitely affected by the limit. We have a limit of 1 over 2n plus 1 times 2n plus 2 in absolute values. At this point, it's not really a big deal, but I do want to point out that x squared, well, that's never going to be negative. So the absolute value of x squared is really kind of redundant. We don't need to write the absolute value symbols. We can just write x squared. But then we're left with this limit. Now, as n approaches infinity, the denominator is definitely going to be going toward infinity. The numerator is going to be stuck at 1. When we take 1, cut it into infinitely many parts, we are left with 0. And x squared times 0, no matter what value of x you get that this is 0. So, what we've just concluded in all of this is that the limit, as n approaches infinity, of the absolute value of a sub n plus 1 over a sub n, that's 0. No matter what value of x is, we get 0. This is always less than 1. So, by the ratio test, the sum, as n goes from 0 to infinity, of negative 1 to the n, times x to the 2n, over 2n factorial. This is equal, not equal to, by the ratio test, this converges for all x. Well, what does this mean about the domain? This says that doesn't matter what x is. X can be anything it wants. So the domain of our function c of x, this is actually all real numbers. Even though it's not asked for, we'll just kind of note that all real numbers, just like up here with the 0, all real numbers can absolutely be represented as an interval. It is the interval from negative infinity to positive infinity. All right. These are fairly in-depth problems, so that's where we're doing a whole bunch of examples before giving you an exercise to work with, but if you would like, you can definitely pause and try to work this example out as an exercise, but I do promise you this one is quite a bit different, so let's just roll into it. What is the domain of this particular function f of x, which is 2x plus 1 to the power of n, divided by n? I actually then want to ask, what is the center of this power series? Now, we were talking about before that the center of a power series was kind of like the halfway point between the endpoints of the interval. So we noted that the center of the power series in example 1 for g of x, halfway between negative 1 and 1 was 0. Well, halfway between 0 and 0 is 0, so we can even say the center in this particular case is 0. We don't really have an idea of what's the center or halfway point between negative infinity and infinity, but we can kind of think of it as 0, but I'm actually not even going to write that down because that's kind of nonsensical to say. But we will actually argue later on that the center of this particular power series is indeed 0. But let's try to find the domain before we figure out what the center of this power series is. So, here we have 2x to the plus 1 to the power of n divided by n. This is not a geometric series, so we don't want to use a geometric series test. The next best thing to try is, well, let's try the ratio test again. We're going to be looking at a limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. In this case, we get a limit as n approaches infinity of, well, a sub n plus 1. That's going to be 2x plus 1 to the power of n plus 1 over n plus 1, multiplied by the reciprocal of a sub n, which is n over 2x plus 1 to the power of n. So here's our limit for the ratio test. Now, just like everything we've been doing before, let's try to simplify this. This is a limit as n approaches infinity of the absolute value of, well, n over n plus 1. Those don't cancel at all. We can always cancel factors, but we cannot cancel terms. That's simply just n over n plus 1. But then we have the 2x plus 1 to the power of n plus 1 divided by 2x plus 1 to the power of n. Remember from our laws of exponents that this says that we should subtract our exponents. N plus 1 minus n is just 1. And remember again that 2x plus 1 has nothing to do with n. Because we're taking a limit as n approaches infinity, we can kind of factor this 2x plus 1 out, but it is inside of an absolute value, so when it gets factored out, it comes with an absolute value. And then we have a limit as n approaches infinity of n over n plus 1. Now, the limit as n approaches infinity of n is infinity. The limit as n approaches infinity of n plus 1 is infinity. So if we think about this like a continuous function, then we have an indeterminate form. We have an indeterminate form of type infinity over infinity, so we can use L'Hopital's rule. And we're left with the absolute value of 2x plus 1 multiplied by the limit as n approaches infinity of n over n plus 1. Take the derivative of n, we get 1. Take the derivative of n plus 1, we get 1. And now that we have a limit as n approaches infinity of 1, well, that's just 1, and we get that our limit in the very end is the absolute value of 2x plus 1. Again, we are saying that the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. That's equal to an absolute value of 2x plus 1. Now, remember that the ratio test says if this limit is less than 1, then we get convergence. If this limit is greater than 1, we get divergence. So, when the absolute value of 2x plus 1 is less than 1, this series converges. So let's solve this inequality. Again, I mentioned that you should have some comfort switching between absolute value inequalities and some nested inequalities. If not, I would definitely recommend getting a little bit of practice with that. But here we go. The absolute value of 2x plus 1 is less than 1 is the same as the nested inequality. Negative 1 is less than 2x plus 1, which is less than 1. When we solve this inequality, we can subtract 1 from all three of these pieces. We get negative 2 is less than 2x is less than 0. And when we divide everything by 2, we get negative 1 is less than x is less than 0. This tells us that the series converges for all the x between negative 1 and 0. We also know that when this absolute value of 2x plus 1 is greater than 1, this series diverges. Now, so when this inequality is greater than 1, we are going to get that this series diverges for all the values outside of negative 1 to 0. So it's going to be divergent from negative infinity to negative 1, and also divergent from 0 to infinity. Now, this isn't a comment that we're going to always make, but I just want to really write it out very specifically in this case, because here we have one part of the ratio test when our limit is less than 1. We have one part for when our limit is greater than 1. But remember what happens when the absolute value of 2x plus 1 is actually equal to 1. When our limit is equal to 1, the ratio test is inconclusive. So we actually need to figure out a little bit of extra information about this. Now, absolute value of 2x plus 1 equals 1 can be split into two different equations. That is, 2x plus 1 equals 1, or 2x plus 1 equals negative 1. This leads us to subtracting 1 from both sides on the left 1, dividing by 2, and we get x equals 0. Over here, we subtract 1 from both sides, divide by 2, and we get x is negative 1. But I want you to actually just really notice that these are the exact same x values that we got in all of our interval limits above. What all of this is supposed to really lead us to is this one big fact that we must check the endpoints. The ratio test is really nice because it tells us that our series, our power series, definitely converges here, but what happens at negative 1? What happens at 0? These must be checked. And so, when we check them, we say, what happens when x equals 0? Well, when x equals 0, going back to our original series, the sum as n goes from 1 to infinity of 2x plus 1 to the power of n over n. When x equals 0, we have a sum as n goes from 0 to infinity. Sorry, said as n goes from 1 to infinity of 2x plus 1. Well, that's 2 times 0 plus 1 to the power of n over n. Well, that means that we get a sum as n goes from 1 to infinity of 1 to the power of n, which is just 1, over n. And we should have a series that's pretty familiar. This is the harmonic series. And the harmonic series is a nice notorious series that diverges, which means that our series diverges when x equals 0. On the other hand, we have the other endpoint of when x is negative 1. So we get a sum as n goes from 1 to infinity. Same thing, but we're replacing x with negative 1 instead of 0. And 2 times negative 1 is negative 2. If we add 1 to that, we get negative 1. And what we end up with is a fairly familiar series. Negative 1 to the power of n over n. This is the alternating harmonic series. And this series, unlike the harmonic series, actually converges. So there's a pretty good reason that we did all of that previous work and all those other videos, because now we're able to actually conclude that this particular series, our power series, converges when x equals negative 1. So the ratio test was really nice because that one test allowed us to make 3 very different conclusions, but they all work together to say the same thing. That our series converges for all values between negative 1 and 0. It diverges for all values outside of that. And then we have to do some extra tests. And these tests might go with the comparison tests, might go with the limit comparison test, or alternating series test, or the integral test, or geometric or p-series, any one of those other tests that we've talked about. But these particular endpoints must be checked, especially knowing that one of those endpoints diverge, one of those endpoints converge. So our domain is a set of all x values for which our series converged. It converges between negative 1 and 0. It converges at negative 1, but it diverges at 0. So here is our domain. Awesome. There was one last part of this question that said, what is the center of this power series? There's a couple ways to think about the center. The center will always be halfway in between the endpoints of our domain. So the center in this case will be halfway between negative 1 and 0, which is negative 1/2. Another way I like to think about it is that our center will be whatever x value will make this 2x plus 1 the thing that is raised to the power of n, because power series have x minus a to the power of n. So it's the x stuff raised to the power of n. You want to know what's going to make this 0. In this case, if we have 2x plus 1 equals 0, subtract 1 and divide by 2, and we would actually get x as negative 1/2. This leads us to the exact same conclusion, that a is negative 1/2. Lastly, we could actually try to factor this into some sort of a form where we have x minus something to the power of n. So taking a third try at this, we have 2x plus 1 to the power of n. We want 2 by itself, so we can factor, or we want x by itself, so we can factor out a 2. We have 2 times x plus 1/2 to the power of n. When we distribute that n, we have 2 to the power of n times x plus 1/2 to the power of n. Lastly, we want to make sure that we have an x minus something, so we can take 2 to the power of n. We can change adding 1/2 to subtracting negative 1/2. So we can see for a third different way that our center is negative 1/2. Depending on how much rigor you want to show, you might want to choose one of these methods over another, but all three of these different methodologies help to support the conclusion that our center is at negative 1/2. All right. So why don't you take a few moments, go ahead and pause this video, and try exercise 1 out on your own. Alright, so let's try this out. Just like before, unless we have a geometric series, we typically want to just kind of start out with, let's try the ratio test, because it's very definitive. It tells us when it converges, it tells us when it diverges, and then we do have to remember, always, check the endpoints. I'll even write that here as a nice little reminder. Check the endpoints. So, let's try the ratio test. We're taking a limit, as n approaches infinity, of the absolute value of a sub n plus 1, which is going to be negative 3 to the power of n plus 1, x to the power of n plus 1, divided by the square root of n plus 1, multiplied by the reciprocal of our original summand, which will be the square root of n plus 1, over negative 3 to the n times x to the n. So, let's see what happens here. We're finding this limit. We want to cancel as much as possible. Now, if we have a negative 3 to the n plus 1 divided by a negative 3 to the power of n, that should just leave negative 3 to the power of n plus 1 minus n, or rather, just negative 3. We have an x to the power of n plus 1 divided by x to the power of n. That should just leave an x. But then we're left with this square root of n plus 1 on the top and square root of n plus 2 on the bottom. I'm going to just place the square roots above and below each other because they seem like they probably go together. Now, just like the previous few examples, we want to notice that, well, this negative 3 doesn't rely on the n, so this negative 3 doesn't really have any place with this limit. Same with the x. And so we can kind of pull this negative 3 and the x out of the limit, but it does come along with those absolute value symbols because they are in absolute values. But we are left with the limit as n approaches infinity of the square root of n plus 1 over the square root of n plus 2. Now, this is probably something I should have commented on a little bit earlier, but when we take n, remember n is going to be a positive value, and so we have n, which is positive, and we're going to add 1 to that, so it's going to be positive. Then we're going to take the square root of that, so our numerator, right inside of these absolute values, that's going to be positive. When we take n, which is positive, and add 2 to it, it's going to be positive, and when we take the square root of that, that's going to be positive, so the denominator is positive. If we take the positive number and we divide it by a positive number, we get a positive number. So the absolute values don't affect this expression at all. So we can actually get rid of those absolute values. We don't need them. which is nice because it allows us to actually utilize information about limits. So let's go ahead and simplify this. Absolute value of negative 3x. Well, the absolute value of negative 3 is just 3. The absolute value of x, well, it actually is just the absolute value of x. And then we're left with this limit. Now, when we have the limit of a square root divided by a square root, well, square root divided by a square root can be written as the square root of the quotient, n plus 1 over n plus 2. And remember, if we think about this as a particular continuous function, the continuous function square root of n plus 1 over n plus 2 is continuous for all values of n except for negative 2. That's fine. N starts at 0. It doesn't ever go to the negative values. We can actually use some limit laws. The one in particular that I want to use here is the limit of a square root is a square root of the limit. And so we can put this limit inside of the square root. And we have a limit as n approaches infinity of n plus 1 over n plus 2 inside the square root. Here, when we're looking at the limit as n approaches infinity of n plus 1 over n plus 2, we should actually hopefully be able to recognize this as a 1 at this point, but to see some of those details, we can use L'Hopital's rule because we do have an indeterminate form of type infinity over infinity. In any case, the limit is 1, and the square root of 1 is just 1. And so what we end up with is the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. That's equal to 3 times the absolute value of x. Now we're trying to determine when this thing is less than 1 because that's what tells us from the ratio test when this series will converge. So we're looking at 3 times the absolute value of x is less than 1. We want to determine when this is actually a true statement. Translating this absolute value inequality into a nested inequality, we have negative 1 is less than 3 times the absolute value of x, which is less than 1. I should actually back up and say, technically this isn't necessarily a full absolute value inequality just yet. In order to be a little bit more precise, we should divide both sides by 3, and so that we have an absolute value of x is less than 1/3. And now we have an absolute value inequality, where we have an absolute value is less than something else. This turns into the nested inequality, negative 1/3 is less than x is less than 1/3. Which is nice because it actually puts it immediately into interval notation, negative 1/3 to 1/3. But this is not necessarily our domain. It might be, but it's not necessarily our domain because of the one big reminder: we need to check the two endpoints. So let's go ahead and do that. We know that it converges for all values between negative 1/3 and 1/3, but we don't know exactly what happens at negative 1/3 or at positive 1/3. So let's look at that over here. What happens when x is negative 1/3? Well, we're going to end up with a sum as n goes from 0 to infinity. The denominator is simply a square root of n plus 1, but the numerator is a negative 3 to the n times negative 1/3 to the power of n. Here, we have a negative 3 to the n times a negative 1/3 to the power of n. We have the same exponent with differing bases. They are multiplied together, which means that we can actually combine these into one single exponent. We have a negative 3 times negative 1/3, negative 3 times negative 1/3. This whole thing is raised to the power of n. The denominator is still a square root of n plus 1. Negative 3 times negative 1/3, well, that's just 1. 1 raised to the power of n is just 1, and so we have a sum as n goes from 0 to infinity of 1 over the square root of n plus 1. Now at this point we want to kind of pull back into our bag of tricks and think of all the different series convergence or divergence tests. To me, this looks very similar to a p-series, but turns out I'm going to go with a trick that's kind of a little bit less conventional, or rather, not one that we may have seen before. If we look at this series, a series as n goes from 0 to infinity of 1 over the square root of n plus 1, when we write these terms out, when we plug in 0, then we get 1 over the square root of 1. When we plug in 1, we get 1 over the square root of 1 plus 1, well that's square root of 2. When we plug in 2, we get 1 over the square root of 3. And we continue this pattern. Well, this looks a lot like a sum of 1 over the square root of n. But n doesn't start at 0, n starts at 1 in this case and goes to infinity. And so these two series are exactly the same. Over here, instead of a sum as n goes from 0 to infinity of 1 over the square root of n plus 1, we can view this as a sum as n goes from 1 to infinity of 1 over the square root of n. Now this series actually is a p-series. The series right above it, this one, looks like a p-series, but it's not a p-series. We'd have to use some sort of a comparison or limit comparison test on it. And it turns out the comparison test would not be conclusive. We would have to go with a limit comparison test. But this series actually is a p-series. This is a p-series that diverges as a p-series with p is 1/2, which is less than 1. It's actually even less than or equal to, so it does diverge as a p-series. So we can actually conclude that negative 1/3 is not part of the domain. But now we should check positive 1/3. So let's see what happens when x is 1/3. When x is 1/3, we have a sum as n goes from 0 to infinity of negative 3 to the power of n times 1/3 to the power of n over square root of n plus 1. And just like before, we can combine the bases and we get negative 3 multiplied by 1/3. That's actually not just 1, but negative 1 to the power of n. And we're dividing by this by the square root of n plus 1. Now this series is not really a p-series, but this is actually an alternating series. We have an alternating factor with this negative 1 to the power of n, and then we have this kind of what's left stuff. So let's go with trying to use the alternating series test. The alternating series test says let's test the sequence 1 over the square root of n to see if this sequence is positive, see if this sequence is decreasing, and see if this sequence goes to 0. Now, the denominator is taking n, and n in this case starts at 0. If we plug in 0, we get 1. Take the square root of 1, we get a positive value. If we plug in 1, we get 2. Take the square root of 2, and we get a positive denominator. Turns out every single denominator that we will ever have is positive. When we divide 1 by a positive number, we get positive. So this sequence is very clearly positive. Just to write that out, we have a sequence of 1 over the square root of n plus 1. And I'll say this is positive. Now the denominator just keeps getting bigger and bigger and bigger with every single new index. When n is 0, and then when n is 1, the denominator gets bigger. When n is 2, the denominator gets bigger. Because the numerator never changes, we can actually conclude that this is a decreasing sequence. And as n goes toward infinity, the denominator approaches infinity, the numerator just stays 1, so we have 1 being cut into an infinite number of pieces. So we get that its limit is 0. Where were we? Back up here. Sorry about that. Because its limit is 0, because it is positive, and because it is decreasing by the alternating series test, we can actually conclude that the sum, as n goes from 0 to infinity, of -1 to the n over square root of n plus 1 actually converges. This series came about from x being 1/3, so we can actually include 1/3 as part of our domain. So, in the very end, when we're looking for the domain of this particular series, we found that this series converges for all values between -1/3 and 1/3. It diverges at -1/3, and it converges at positive 1/3. So we can actually conclude that the domain is -1/3 to 1/3, with 1/3, and without -1/3. Cool. So we've done 5 different problems here, and something that we've hinted at but is actually really important to notice is that every single time that we've looked at the domain, we've gotten an interval here. We got a very uninteresting interval, but we got an interval here. We ended up with an interval here. We actually ended up with an interval here. And even in this problem, we ended up with an interval. Now, sometimes we include the left end and we exclude the right end. Sometimes we include the right end and we exclude the left end. Sometimes we include both of those ends. Sometimes we exclude both of those ends. But the big thing to remember here is that and the big thing to point out here is that every single one of these domains has been some sort of an interval. Maybe open, maybe closed, maybe half open or closed, but we actually want to summarize that all in this theorem right here. Before we do that, let's go ahead and jump into a quick technology exploration, and let's look at what the graph of one of these looks like. Let's look at the graph of c of x. Now, again, we're kind of limited with functionality in Desmos. We can't look at a sum as n goes from 0 all the way to infinity, but we can look at some partial sums and maybe get an idea of what this particular graph looks like. So, let's try that out. Alright, so we are trying to graph -1 to the n, x to the 2n, over 2n factorial as n goes from 0 to infinity. Let's try this out in Desmos. So let's actually call this c of x just because that's what we've been calling it. This is a sum. Remember in Desmos we actually want to make n a slider because we are finding nth partial sums, so I'm going to change that lower index to an I. We're not starting at 1, we're starting at 0 in this case, and Desmos can't really handle the infinity, so let's go to n. And this can be, we're looking at a sum as we have -1 to the power of I times x to the 2i, all of this over 2i factorial, and we do want to make sure that n is indeed a slider. And let's slide it from n, in this case we want to start at 0, and let's just go to 40, say. We'll make a step size of 1. And let's go back to, here's at 0. So, in this case we're trying to figure out what this particular graph kind of looks like. This first partial sum looks like well, it's a line. If we start to increase the values of n, Let's go ahead and slow that down, start that over again. Then, well, here's what all the different partial sums look like. Here's when n is 15. We saw earlier values of n. We can keep increasing its value. Doesn't look like we're getting much change right here, but kind of saw that the change was going outward. So let's go ahead and just squeeze this a little bit. And let's keep watching this change. Oh, I lost it. There we go. As n keeps getting bigger and bigger, it looks like, well, that inside part just kind of keeps staying the same, but the outside just keeps kind of growing. Does this graph look familiar at all? I hope it kind of looks familiar. Maybe not with the outside parts. Let's just zoom in again on the inside. If I were just to provide you with this particular graph, I would hope that it might look, if nothing else, kind of familiar. Maybe we can change the axes to make it a little bit more familiar. Let's go with a step size, not of 1, but maybe pi over 2. So we have this periodic function. It's a periodic function that looks like it has a period of maybe 2 pi. And it's going from the top at 1 down to -1, back up to 1. We have this periodic wave-looking function that starts at 1. I don't know about you. I think this looks like cosine. But it's not really exactly cosine, because if we go out to the outside, well, clearly cosine doesn't just kind of drop off at the end here. But if we again kind of observe this pattern about what's happening with these values of n increasing, remember, an nth partial sum is an approximation. So what we're doing is we're approximating this function, and our approximations should get better as n increases. And as n gets bigger and bigger and bigger, looks like this kind of series keeps approaching something. The nth partial sums, to me, look like they are approaching cosine, but it's not really exactly equal to cosine, at least not just yet. But we were asked some questions over here, and it said, what familiar function does c of x look like? I don't know about you. I think it looks like maybe cosine of x. And then it asks, does the domain found in the previous example seem accurate graphically? Well, here, it's taken a while, but the domain does keep getting, to me, it seems like more and more accurate. Let's compare this with maybe one of our other functions that we were looking at. Let's go ahead and just reload this. Now the first example we were looking at, we call it g of x. That was equal to a sum. And again, we want to change this to an I going from 0 to n of, the first one we were looking at was x to the power of I. Want to again make a slider, and going from 0, let's say to 40 again. I will let you know that depending on the processing power of your computer, you may want to choose either larger or smaller values for n, because the larger it gets, it actually kind of breaks some computers. Desmos can't handle a lot of the computing power, so just be careful. Now in this case, we found a domain of, well, let's go back and check. For g of x, our domain, we're way up here, it said -1 to 1. So, if we come over to here, it looks like this function exists outside of -1 to 1. There's values over here in -5 and +5, but this is just the first term of our series. So let's increase this. Well, the more terms we get, it looks like our series is actually kind of shrinking. And I don't know about you, but it looks like it's kind of hanging out somewhere between -1 and 1. Right now, this series is going to the further to the left of -1, and well, if I zoomed up enough, I'm sure it would go a little bit to the right of 1, but the further I keep making n, it keeps shrinking. To me, this very much looks like it should make sense that the domain is -1 to 1. This is an idea that we'll be exploring in the next couple of videos, but just a little teaser right now. Alright, let's go back into this theorem. So, our theorem here and then the following definition is really meant to try to summarize all of the work that we've done in these first 4 examples and your exercise. When we are looking for the domain of a power series, it looks like we should end up with an interval. But we have very different sorts of intervals. And in fact, when we're given a power series centered at A, and we write our power series out maybe this way, there really are only 3 different possibilities. This series converges only when x is actually equal to A, its center. That was an example that we saw way up here with example number 2. We had that the domain of this function was actually just 0, the center of this particular power series. The second option is that the series converges for all possible values of x, all real numbers. That was the result that we saw with this function that seems like it's the cosine function. Our particular power series converged for all real numbers. And then there's this third possibility, which is that there's going to be some number r, so that the series converges for all of the absolute value of x minus the center is less than r, and it diverges for all of the values outside of that. And then we're actually not quite sure what happens when x minus a in absolute value is equal to r. This last result summarizes a lot of what we've been doing in these previous examples, just like your exercise. We ended up with some sort of an r value. In this case, it looked like our r value may be 1/3. And our center, in this case, was actually 0. So what we ended up with was an absolute value of x minus 0 was less than 1/3. In this case, r was 1/3. We found that this series converged when the absolute value of x was less than 1/3. It diverged when the absolute value of x was greater than 1/3. And then the series, it converged at positive 1/3 and it diverged at negative 1/3. But that was something that we actually had to check when we checked the endpoints. It turns out these different ideas, these different concepts do have names. In our case, the number r is called the radius of convergence, and the interval that results in that is called the interval of convergence. In all of these cases, in these 3 different cases that we found above, in the first case, when our radius of convergence was 0, that was that n factorial power series, then our interval of convergence, when it converged just at a, well, we can look at a as being an interval, an uninteresting one, but an interval from a to a. When we had that the series converged for all real numbers r in R, it turns out that the interval of the radius of convergence is infinitely large, and we actually say that the interval of convergence is all real numbers. So the first example we had, or first idea we had here, was that if the series converges only when x equals a, then the radius is 0, and we said the interval of convergence is a to a. When the series converges for all x in all real numbers, we say that the radius is infinity, and the interval of convergence is negative infinity to positive infinity. And in the third case, when we have to actually test our endpoints, we have 4 different possibilities. We've seen a number of these already, but here are 4 different possibilities. We get convergence between a minus r and a plus r, but we have to check the endpoints. We could have that neither of those endpoints is included. We could have the right endpoint is included, but the left point is excluded. We could have that the left point is included, or the right point and the right point is excluded. Or we get that both the left and right endpoints are both included. Each of these cases, again, happens from testing the endpoints. So, let's actually revisit all of our previous examples. In example 5, I want to actually go back to all of the previous examples and actually determine what is the radius of convergence and what is the interval of convergence for the following series. And then let's actually graph the domain on some particular number line. So, for g of x, which was summing from n equals 0 to infinity of x to the power of n, we actually found that this particular function, this particular power series, had a domain of -1 to 1. In this particular case, this was born from having the absolute value of x being less than 1. When the absolute value of x is less than 1, this is really the same as saying absolute value of x minus 0 is at less than 1. And the only reason we write this is that we want to include some idea of a center. In this case, our center is 0, because the absolute value of x is the same as the absolute value of x minus 0. In this case, the number 1 plays the role of our radius, and so we can actually come in here and say that the radius is 1. Let's change that to the other blue just for consistency. The radius of convergence is 1. The interval of convergence, that actually happens to be exactly the same thing as our domain, which is kind of nice. We have -1 to 1. Now, if we were to graph this on a number line, then, well, we have -1. Oop. Sorry about that. We have -1, we have +1, and we're looking at all of the values between -1 and +1, not including either of those endpoints. There is our graph. And just out of curiosity, let's go ahead and find the center. The center was here at 0. Now, I'm just going to go ahead and shift this graph downward just a bit. Let's zoom in on this and say we have the graph from -1 to 1. We're including everything in between. Now, we use this term radius, and that may seem kind of weird because we typically have a radius when we have something that is circular, and here I don't see any circles. Unless you want to think of the number 0 as a circle, but we don't have any circles. But that's because this idea of a radius of convergence does absolutely go beyond the scope of what we are going to be talking about in these videos. Radius of convergence actually comes from a larger idea where we would look at series not just on the real numbers, but in maybe complex numbers or in other sorts of number systems. In the complex numbers, when you graph complex numbers, we won't be doing this, but just want to point out, when you have complex numbers, you actually need an entire plane. And so we wouldn't just have kind of a horizontal axis, but we would often have some sort of a vertical axis as well. And when we have this vertical axis, we would be looking at complex numbers, which aren't just sitting on this line, but they would be in an entire plane. And when we look at a radius of convergence with complex sequences, we don't just look at how far to the left we go, how far to the right we go, but we actually find a center, and then we go around that center. In this case, we'd be looking at a unit circle. And this unit circle absolutely does have a radius. Its radius would be 1, but if we were to ignore all of these ideas here, if we were to ignore the complex plane, then all of those radii talk, all of those circle talks, really just come back to a number line between -1 and 1. So that's where this idea of a radius of convergence really comes from. It comes from multiple dimensional graphing. But here, we're just looking at this particular number line. But hopefully this helps to give some insight as to why we talk about a center of a power series and a radius of convergence. Because if you go from a center out a certain amount, we call that a radius, and we should be end up with some sort of an interval. The actual boundary points, we do actually have to check. I do want to label this particular number line. Our variable is x, and so this is a number line for x's. Let's keep going. We found that our domain for z of x was n factorial times x to the power of n. This domain was just 0. And so in this case, our radius is the distance from the center. We found that our center was here at 0. The distance from our center to the endpoints, well, our endpoint is really uninteresting. We just have the point 0. The distance from 0 to 0 is 0, and so our radius actually is just 0. Our interval is just the closed interval from 0 to 0. Kind of an uninteresting idea, but consistent with our theorem and our definition as is here. Our radius of convergence was 0 because our series converge only when x is equal to 0. Our interval of convergence is also 0 to 0. For c of x, we found that our domain was all real numbers. And so this corresponds to having a radius of infinity, because when we're graphing all of our values of x, we can start at 0, but we go all the way to the right an infinite amount, all the way to the left an infinite amount. The graph of our domain is kind of like the opposite of what we did in part B here. It's all the way to the left, all the way to the right. It goes infinitely far in both directions. It gives us an interval of negative infinity to positive infinity. You could also write that as all real numbers. Lastly, when we looked at f of x, was the sum as n moves from 1 to infinity of 2x plus 1 to the power of n over n. Now notice that all of our other power series started at n was equal to 0, but this one actually started at n is equal to 1. I'd encourage you to think about exactly why. Like, what would actually happen if n was equal to 0 in this last particular case? Well, if n was equal to 0, we'd be dividing by 0 here. That can't happen, so in order to kind of fix that, we just decided let's start this at 1 instead. Well, we found that our domain in this case, I don't quite remember, so let's go up and review that one. That was here in example 4. We found that our domain was negative 1 included, 0 excluded. So our domain, negative 1 to 0. On a graph, this means that we look at going from negative 1 to 0. We included negative 1. We excluded 0. Here is our graph. We had also identified that the center of this particular series was at negative 1/2. And our radius should be the distance from the center out to the boundary. In this case, the distance from the center to the boundary would be 1/2. So, because our distance here was 1/2 from the center out to the endpoints, we can actually conclude that our radius of convergence is 1/2. Our interval of convergence, again, that's the same as the domain. We typically have to go through and determine when this converges, when this diverges, and then make sure to check those endpoints. We've already done all of that work, so we're good on that one. Last thing I want to make sure that you can actually identify a pattern here is that when we look at a radius of convergence compared to its interval of convergence, the radius is always going to be half of the length of the interval. And that's because we are taking and thinking of this like a diameter. And if we think of this as kind of like a, quote, diameter of convergence, if we cut that in half, we get a radius, and that's going to give us 1/2 on each side. For all of the previous examples, that should work in the same way. If we were to look at -1 to 1, this interval has a length of 2. Half of 2 will be 1 on each side. So, here's how we can go through and find a radius of convergence and a corresponding interval of convergence. I want you to take a few moments for this last exercise. This is the same series as you had dealt with before. I want you to pause this video and try this one out on your own. Alright, so let's see how this last example works. Here's our exercise. Let's find the radius of convergence and the interval of convergence for the series below, then graph its domain on a number line. Well, normally this question, this particular exercise would take quite a while to go through, but we have spent some time, and we already found the domain. If you're ever asked to find the interval of convergence and the radius of convergence, then you're really just being asked some specific information about the domain. So you want to find the domain of your particular power series. In this case, we found that the domain was -1/3 to 1/3, excluding the left side, including the right side, and the domain is already the same as our interval. The interval of convergence was -1/3 to 1/3. We excluded the left side. We included the right side. From here, we can graph this. We have a -1/3. We have a +1/3. And when we're graphing this, we want everything in between. We want the right side. We do not want the left side, so we exclude that. And from here, we can obtain our radius of convergence. Our radius should be half of the length of our interval. Our interval has length 2/3, and so half of 2/3 is 1/3, and so our radius of convergence indeed is 1/3. Again, another way to see this is that you can find the center, and you can say how far out from the center is it to the endpoint. Turns out it's 1/3 on both sides. And the very last way that we actually want to make sure that we can identify this, and this is based on the definition, is that if we come back, we want to look at this particular inequality, the absolute value of x being less than some value. That value on the right side of your inequality is your radius of convergence. That is exactly what the definition actually mentions above. It's already circled here. Circle it again. Absolute value of x minus a is less than r, where r is our radius of convergence. The rest of these videos for sequences and series are very much going to pertain to power series and trying to relate power series back to functions. So this stuff will be focused on quite heavily. All of the other series and sequence information and tests and all of that really trying to pay service to power series. And we're going to develop power series quite a bit more in the next couple of videos. So, thank you.